Hello everyone. So these are the notes for 9.3 in Calc 2. So when we were looking at how to solve first order linear equations or differential equations, we were looking at how we could solve these things, right? And I showed you how to, solve these basic things by using an integrating factor and then going through that process. But what we're going to look at in this section is, excuse me, we're going to actually look at some word problems that arise from those kinds of differential equations. And the one that I'm going to focus on in this section more than anything is mixture problems. Those are the ones we're going to look at in this problem, or in this section of notes, 9.3. So mixture problems. So how do we do this? So what we're going to do is we have to find a way to create a differential equation, right? A first order linear differential equation. If you think back to the original chapter 7, when we did separable differential equations, we looked at word problems that arose from those. If you recall from earlier in the class, like in chapter 7, I'll just jot these down here for your reference. We looked at separable. Right? And if we looked at some of those word problems that came from there, well, exponential growth and decay. We also looked at Newton's law of cooling. Right? So those are just some examples of word problems that came from separable differential equations. But mixture problems arise from first order linear differential equations. So these arise from first order linear ODEs. Just remember, separable differential equations are also first order ODEs, but remember, there are two different types of differential equations. Like this one could be, separate them, integrate. This one you need an integrating factor. So mixture problems, they arise from first order linear ODEs, which require an integrating factor to solve. Sometimes that's not true, but generally most mixture problems, as you'll see, will require the methods we learned in 9.2. So how do we make these things? So how do we devise how to construct and first order linear ODE. How to construct a first order linear ODE. So how do we do this? Let me underline this whole thing. So here's what we're going to do. So definition. So basically we're going to have to identify a lot of different facts here, a lot of different variables and functions to construct a first order linear ODE. if you remember, what does a first order linear ODE look like in standard form, right? What does it look like in standard form? It looks like dy dt plus p of t times y equals what? Q of t. All right. So remember, that's what a first order linear ODE looks like. And that's in standard form. So we got to make this kind of equation from a word problem. That's what we're dealing with here. This is something completely different. This is a totally different type of differential equation. But they're both first order. It's just they're solved differently. This one's separable. This one needs an integrating factor. So here's what we're going to do. We're going to let y. So in these mixture problems, we're usually interested in finding how much stuff is in a given container. It could be a tank, a vat, whatever. So we're going to let y, which is a function of t, but we're just going to let y, we're just going to use y, but it really is y of t. We're just going to write it this way so it's easier to write out when we make the equation. We're going to let that be the amount of stuff in a container at any time t. All right, so we're going to let y, or y of t, be the amount of stuff in a container at any time t. So there's a lot of things we need to consider here, but I'm going to collect everything we need on this sheet. So if we know this, then what does dy dt represent? What does dy dt represent? Because that's this part right here in the equation, isn't it? So the amount of stuff is right here, right? That's the amount of stuff. What does this part represent? This is the amount of stuff. This represents what? That represents, or it measures, the instantaneous change, because that's what it is. Dy dt is that's their instantaneous change, right? The instantaneous rate. You learn that in Calc 1. Derivative is the instantaneous rate of change. That measures the instantaneous change in amount of stuff. At any time t. Right? If this is the amount of stuff, well, this is how much stuff is changing at some specific moment in time. Right? Is the amount of stuff going in increasing or decreasing? That's what dy dt is. All right. That's the change in stuff. Okay. So if we're interested in, if we're interested in how much stuff is in the container at any time, then we want to see how much this changes. So our ODE can be found as the following. So this is the amount of stuff in the tank at any time, right? So the amount of stuff coming in the tank and leaving the tank, that could change. So this is constructed as the rate in minus the rate out. So this is basically the framework of the differential equation that we're trying to find. We're going to talk about how we find each one of these terms in a minute. But you know, the rate of the stuff coming in minus the rate of the stuff leaving, that'll measure the amount of stuff in the tank at any given time. Okay, so what is the rate in? What is the rate in? So the rate in is the concentration at time t multiplied by the inflow rate. So you'll see what I mean when we make these problems, but if stuff is coming into the tank, right? That stuff could be pure water. It could be a mixture of water and the stuff we're trying to find, right? So that concentration times the rate at which it's flowing in is going to give me my rate in term right here. The rate out is a little more sophisticated. It's not too bad, but there's a little bit more to it. The rate out is measured as y over v of t times the outflow rate. And technically this could be y of t as well. So remember, what does y of t represent? What is this amount? That's the amount of stuff at any time. We defined it right here. So if I were to put a star on this, right? That's the star right here. So I do want to talk about, all right, well, what's this? What is that? And outflow rate. Okay, well, outflow rate, that's easy enough to understand, right? That's just how much the stuff is leaving the tank. So if I have it, if this is my tank, and here's the stuff in it, right? Here's a pipe coming into my tank, and here's a pipe that's leaving my tank, right? So stuff is coming in, and then stuff is leaving the tank, right? So here's my mixture, and the mixture contains water or some kind of liquid and stuff, right? The stuff could be salt, it could be whatever, it doesn't matter. So the rate in is stuff coming in the tank, and the rate out is the stuff leaving the tank, right? So the rate in is just the concentration of the stuff times the inflow rate, all right? That comes in, and then the rate out is the outflow rate times this. Well, all this is right here is a concentration at time t, but the rate out is different because it's different than the rate in here, because when this stuff is coming out, it could have a different concentration, right? The concentration coming in here is dependent on nothing. It's coming in. It's at its own unique mixture. But once it gets mixed in with all the stuff here and it comes out, it's going to be dependent on what was in here originally. That's why this quantity right here is not the same as the concentration here. So how do we figure this part out? Well, we already know what y of t is. That's given to us. That's the amount of stuff. So we're just going to let that be y. All right. And v of t, so let me describe that here. Y is just y, the amount of stuff. And v of t is, so like I said here, v of t, well, you could probably guess this, but v is, if the function's named v, it's probably going to talk about the volume. So v is going to be the volume of the tank. So v is going to be the volume of the tank at time t. So how do we figure out what the volume is? So this is found. So the volume is found by, so v of t equals, so I'll call this one smiley face. So how do we find smiley face? Well, so the volume is going to fluctuate, right? As stuff comes in and stuff leaves, the volume is going to either go up or go down depending on how fast it's coming in and how fast it's leaving. So the volume is going to fluctuate. So that depends on, well, it depends on how much is in there initially, right? So it's v sub 0 plus how much is coming in and how much is leaving. So that's going to either make it go up or go down. So that's going to be plus that term, which is v in minus v out, but that's going to be multiplied by t. So that right there is smiley face. So once we figure out this stuff right here, which is given to us in the word problem, we could plug that in here. This is just going to be y. And we multiply that by the outflow rate, which is given to us as well. That'll give us the rate out part of the differential equation. And then the rate in part, which is even easier, is you're multiplying these two quantities, which is given to us in the problem. That gives us our rate in for the differential equation. And then we'll have our differential equation, which models the mixture of the substance in a tank and how much stuff is in it for any given time. So once we find this, then we just need an initial condition. So then the initial condition is y, since y is a measure of stuff, that's going to be the initial condition, where I'll put a t sub 0 here to remember the initial time equals the initial amount, where t sub 0 is at time t equals 0, and y sub 0 is the amount of stuff in the tank at t equals 0. So once we find this and this, we have our differential equation. So then from there, it's just a matter of solving it, which we know how to do. Find an integrating factor and go from there. So yeah, there seems to be a lot to this process. I mean, it does seem like a lot of information. But if you could, you know, see where that comes from and where that comes from in this, you're okay. And then you can make the differential equation and go from there. So let's look at an example. Okay. So, in an oil tank, a storage tank contains 2,000 gallons of gas. Well, of gasoline. That initially has 100 pounds of an additive dissolved in it. Gasoline containing 2 pounds of additive per gallon is pumped into the tank at a rate of 40 gallons per minute. The well-mixed mixture, or I should say the well-mixed solution, is pumped out at a rate of 45 gallons per minute. Question: how much of the additive is in the tank (20 minutes) after the pumping process begins? Alright, so yeah, it's a word problem, and there's a lot to it. There's a lot of information to these guys. So, you know, when we're trying to figure this out, I guess I could have said, this is a bit redundant, in an oil tank, a storage tank. I could have just said in a storage tank, but whatever. So I want to make a differential equation. That's my goal here. All right. That's what I want to do. Okay. So I want to make an ODE. So I start with the basic structure. So dy dt equals the rate in minus the rate out. So now I just got to figure out what the rate in looks like and what the rate out looks like. I'm just taking everything that I jotted down here. I'm just figuring out every piece of this to build my differential equation. And each piece here is in the problem. You just got to find where it's hidden in the problem. You got to do a little detective work. Alright, so remember in your notes, rate in is the concentration at time t. Times the inflow rate. So let's see if we could find that in our problem. So what's the concentration of stuff per gallon in this problem? Let's figure that out. So if you do a little looking here, it's right here, right? Gasoline containing what? 2 pounds of additive per gallon is pumped into the tank, right? So that right there, so this right here, pounds of additive per gallon, 2 pounds per gallon. Those units right there, pounds per gallon, that's a description of a concentration, right? So this is going to be 2 pounds per gallon times, now what is the inflow rate? How fast is it coming in? It's in the same sentence. It's pumped into the tank at a rate of 40 gallons per minute. So that's the inflow rate. Because you can see it, gallons per minute. Gallons, that's an inflow rate. Usually rates are measured in time, right? So that's going to be times 40, what? Gallons per minute, right? So if you do the computation there, well, 2 times 40 is obviously 80, but what are the units? So the gallons cancel, right? And you have pounds per minute. Now, let me, so this right here is the rate in. Great. So that right there I'm going to denote with a star. That's the rate in. Great. So if you look at the, before I go to the rate out, I just want you to look at something. Look at the units here, pounds per minute. What is the differential equation model? The differential equation is modeling, so Y, it's the amount of stuff in the container at any time. Look at the units, the amount of stuff per time. And that's exactly what we're trying to find. We're trying to find the amount of stuff at a given time. And the units are telling us that this is correct. So ideally we want rate out to have the same units when we're all done. And this little mini formula here will give us the correct units, pounds per time, or stuff per time. Okay, so the rate out is Y of t over V of t times the outflow rate. So let's go through this. Well, what did we say Y was going to be? It's just, that's the amount of stuff, right? So we're just going to let that be Y. That'll always just be Y. Okay. V of t, we don't know that yet. I'm going to put that here. I'm going to work on it down here, but we don't know that yet. But do we know the outflow rate? Yeah, we do. The problem has it. So what's the outflow rate? Right here. The well-mixed solution is pumped out at a rate of 45 gallons per minute. That's the outflow rate. So The outflow rate is 45 gallons per minute. Now we don't know what this is yet because we still have to figure out V of t, right? We have to figure out the volume function for the tank. So let's do that down here. So remember, V of t was defined as what? The initial volume plus the quantity V in minus V out times t. Because this could fluctuate. That's why it's being multiplied by t, because this fluctuates as time moves, right? But the initial amount is the initial amount. That doesn't depend on time. So let's figure this out. The problem should give us this information, right? Okay. So what was the initial amount of, now not the initial amount of stuff, the initial amount of mixture in the tank? So it's in the first sentence, right? A storage tank contains 2,000 gallons of gasoline. So that's telling you that's how much the tank contains initially. So there's 2,000 gallons, and right, gallons is a measure of volume, right? So 2,000 is the initial amount. And I'll just put the units there for completion. Plus, what's the volume in? What's the volume coming in? So the volume is changing, right? The volume coming in is the amount of, so, you know, this inflow rate minus the outflow rate of the volume. This right here is going to change the volume, right? So volume coming in is the inflow rate, pumped into the tank at a rate of 40 gallons per minute. That's going to fluctuate the volume. It's going to make it either go up or down. So that's coming in at a rate of 40 gallons per minute. So the volume coming in is going to be 40 gallons per minute minus the volume coming out. Well, it's leaving the tank. That mixture, that solution is leaving the tank at 45 gallons per minute. And that quantity is going to be multiplied by T. Right? And T here, what are the units of T? In minutes. So you can see how the units are going to work out here. So when it's all said and done, I have 2,000 gallons plus, what's 40 minus 45? Well, obviously that's negative 5. So I'm going to have plus, well, I suppose I could have just kept this as a negative. Minus 5, right? So I have 2,000 gallons minus 5 gallons per minute times minutes, which is in T, right? Times T minutes. So I'm keeping the units here just to show you that the units will work out. What is volume measured in? It's measured in gallons, right? So I have gallons for the initial amount, but I have gallons per minute times minutes. Ah, what's going to happen there? The minutes are going to cancel. That's why I have that T out there up front. So when this is all said and done, my volume function is going to be 2,000, and that's in gallons, minus 5, right? Gallons per minute times T minutes. The minutes cancel. So that's going to be minus 5 T gallons. So that right there is the volume function of this problem. So therefore V of T equals 2,000 minus 5T. So that's the measure of how the volume fluctuates once the pumping process starts. So this part right here, so that guy, that's going to go right here. So this right here is going to be 2,000 minus 5t. Now remember how I said earlier the units should work out to pounds per minute? Well, the amount of stuff is measured in what? Pounds, right? What are the units of this quantity? We just got done saying it's gallons, isn't it? Alright, so if I multiply this by this, what happens? The gallons cancel. And I'm left with what? Pounds per minute, which is exactly what I need. So when I multiply this by this, I get y. Well, no, I'm not just going to get y. I have a 45 here, right? I'm going to get 45 times y. All over what? 2,000 minus 5t. And like I said, the units of that are in pounds per minute. So that right there is my next term that I needed, which is right here. So, you know, it seems like there's just a lot of work to go on these problems, and, you know, there are. It's a good chunk of work. But this is what we use. This is how we construct these differential equations. This part isn't hard. It's just a matter of finding the information you need in the problem. But now that I made these two things, I have my differential equation. So let me come up here. So my differential equation, dy dt equals, what's the rate in? It was 80. So now I'm not gonna include the units now, just to make it look a little nicer. So I'm gonna have 80 minus rate out. What was the rate out? Well, we got 45y over 2,000 minus 5t. Here's my differential equation. It may not look like it, but this is a first order linear differential equation. It's not written in standard form. But how do I write it in standard form? How do I write this in standard form? Remember, it's a standard form, right? So I want you to look at this compared to this. It looks close, but it's not quite there. The dy dt here is by itself. So I have plus something containing t times y, right? Well, look at this right here. Isn't this part right here something containing t? Yes, it is. That's for number over 2,000 minus 5t. So that right there is my p of t times y. P of t times y. There's my p of t times y. And that's going to be equal. So if I bring this term over here, I'll have it in standard form. Ta-da! And then that'll be equal q of t. And in this case, q of t will just be 80. So this right here is my q of t. So in standard form, just to add this in standard form, I'm just going to add this to the other side. So I'm going to have dy dt plus this term, 45 over 2,000 minus 5t times y equals 80. Here's my differential equation in standard form. And you can see how it compares. Right? I mean, I did it here, but you can see it now. Dy dt plus p of t times y. Here's my p of t times y equals q of t. And there's my q of t. So that right there is my p of t. And this right here is my q of t. So that's it. So my differential equation I'll just copy that down here. Is that. What do I need though? I'm missing one thing. I need an initial condition, right? So the initial condition is when t equals 0, right? So when t equals 0, how much stuff was in the tank? So y, t equals 0. How much stuff was in the tank? That's what y sub 0 is. That's when t equals 0. How much stuff was in the tank? The problem will give you that information as well. You just got to figure it out. How much stuff? Oh, there it is. The tank initially contains 2,000 gallons of gasoline. That initially has, it's right here, that initially has 100 pounds of additive dissolved in it. That's right there is y sub 0. So I initially have 100 pounds in my tank. So that right there is my IVP, my initial value problem. That's it. So that's how you find it. But we got to answer the question. How much additive is in the tank 20 minutes after the pumping process begins? So now that we found it, now we got to solve it. How do we solve a first order linear ODE? We find an integrating factor. Yeah, I know. These problems are fun, man. So how do we do that? Well, we find an integrating factor. So let's solve this thing. It's in standard form, isn't it? Okay, so what's the integrating factor? It's e to what? To what power? The integral of p of t dt, right? But what is p of t? It's this thing. So that looks nice. So it's going to be e to the integral of that dt. So this looks really messy, but that's what it is. So let's integrate this. That's the integrating factor, right? Okay, so how do we integrate this thing? So we got to integrate it by doing what? U substitution. So I could bring the 45 out, right? And then I'll have 1 over 2,000 minus 5 t dt. All right, so now when I integrate this, right, you could do that with U sub. So you're going to let U equal what? 2,000 minus 5t. And then you're going to get du equals, so that's going to be minus 5 dt. and then solve that for dt. You're going to get du over -5. So when I go through this, yeah, I know these problems are pretty long. You know, they could be, they're very lengthy, but this is Calc 2. So I'm going to have E. Now I'm going to have 45 out here times the integral. And now my integral is going to be what? It's going to be 1 over u. And dt is what now? du over -5. Alright. So, well, that's nice. So I have 45 over -5, which is just -9. Right? So this will be e to the -9 times the integral of 1 over u du. Okay. So now that I have this, well, what's the integral of 1 over u du? That's easy. That's just the natural log of u plus c. So now I'm not gonna include the plus c here. When you're finding the integrating factor, don't worry about the plus c. So I'm gonna have e to -9 of ln of u, right? But what was u? U was just 2000 minus 5t. Okay. I could simplify this further, can't I? Yeah, I could use properties of logarithms. So I could bring this -9 up here and rewrite this as e to the ln of 2000 minus 5t to the -9th power. And then if I brought this whole thing down as a factor using properties of logs, e and ln cancel out. So I'm just left with the quantity 2000 minus 5t to the -9th power. Okay, that right there is my integrating factor. That's what mu of t is equal to. I'm not done yet. That's just my integrating factor. That's what I'm going to use to multiply both sides of this differential equation by. I know, these problems are fun. Now right there's my integrating factor. So now if I go to the next page, let's continue the problem there. So what I'm going to do now is, so now that I found my integrating factor, right, I'm going to take this, I'm going to multiply it to both sides of my differential equation in standard form. So I'm going to take this, I'm going to multiply it to both sides of this. That's what I'll do on the next page. So when you do that, this is what you get. So you're going to have your integrating factor times the left side, which was dy dt plus 45 over 2000 minus 5y, or I'm sorry, minus 5t times y. That's the left side, and that equals, and then you multiply that by the right side, which is 2000 minus 5t to the -9th times what? So you can see what I'm doing here, right? Here's this. That's being multiplied by the left side, which is what I have here. And then I'm taking that and I'm multiplying it by 80 on the right side. So that's what I have now. Okay, well that looks ugly. But again, this is where the magic happens. So if I distribute this in here, let's do that. So I'll have plus. So I want you to see something here. When I distribute this to here, so this is to the negative ninth power. If I reciprocated it and brought it down, here's another factor of it right here. Right here's a single factor of that. So if I multiply this by this, right, I'm really just getting one of these factors. These factors are basically going to combine. So what I'm going to have is I'm going to have plus 45. That times that is going to give me 2000 minus 5t to what power? So if I brought this up and wrote it as -1, right? So -9 times -1, that properties of exponents, that'll give you to the negative 10th power, right? And that's going to be times y, right? Because of the y there. And that equals, so I'll just bring the 80 out front here. Okay. So that's what I have now. Okay, so what's the magic here? What's the magic here? So remember, what's the left side supposed to be when you multiply it by the integrating factor? It's supposed to be the product rule, right? So that's ddt between the integrating factor, which was this, and y. Remember in the previous section when we solved these things, I talked about it there. But so this right here is the product rule. Between those two. And if you're not convinced, go through it. High d low plus low d high. This is the high term. So all right, high, there it is, times d low. What's the derivative of y? dy dt. Right? Plus low, there's the low term, there it is, times d high. How do you take the derivative of this? You use the chain rule, right? So you bring the -9 out front, and then you subtract 1. So I have a -9. It doesn't, you don't see it here yet, but you will. So I have -9 times this to the -10th power. There's the -10th power. And then you multiply the inner, what's the derivative of the inner later? -5. What's going to be -5 times -9? 45. So this is the chain. This is the product rule. And if you're not convinced, go through it. But that's what this is. And that's going to be equal to the right side. So now from here, just integrate both sides. That's where the magic occurs. So you're going to integrate the left side, and you're going to integrate the right side. All right, that could be an integral of this. So what happens here, since I have a product rule, the integral of this product are going to cancel out. So that's the magic of using an integrating factor for these things. It's beautiful. So I have this times this. And that equals the integral of this. Well, how do we integrate this? Well, you can see why these problems are a pain in the butt. So to integrate this, this could be written as what? The integral of, if I rewrite this a bit, 80 over that to the positive 90t, because I brought it down. So I could bring 80 out, right? So I'll have 80 integral 1 over 2000 minus 5t to the 9th dt. How do you integrate this? You go through U substitution again. We kind of did this already, right? We kind of did it over here, but this is to the 9th, so you just go U sub. So you just let U equal 2000 minus 5t again, which we did already. Alright. So then when you do that, you get what? 80 times the integral of 1 over U to the 9th power, and dt is now what? Du over negative 5. Okay, so if I clean this up, I have, well, 80 over negative 5 is what? Negative 16. So this will be negative 16 integral. Now if I brought this up, I can make this u to the negative 9th du. So now when you integrate this, you just use the power rule. So it's negative 16. When you integrate this, so you're adding 1 divided by a new power. So if I add 1 to negative 9, I get negative 8 and divide it by negative 8. So that'll be negative 1/8 u to the negative 8 plus c. So this is just to integrate the right side, and then we got to solve for y. So yeah, these problems are fun. Well, negative 16 times negative 1 over 8 is what? Positive 2. So that'll be u to the negative 8 plus c. But what is u? It's this quantity. So when it's all said and done, this will be 2 times 2000 minus 5t to the negative 8 plus c. So that is not the solution. That's just the integral of the right side. So that goes here. Okay. And that's what the book has. So now, how do I solve this finally? One more step. Divide through by this. So then you get y by itself, which is what we were trying to do. This cancels out with that. So I have y as a function of t Well, when you divide this by both terms, so you have a 2, right? But what happens here? So I have this to the negative 8th divided by this to the negative 9th. So what? That's going to be this to what power? Just using properties of exponents. Negative 8 minus negative 9 is negative 8 plus 9, which is 1. So this will be just, what, 2 times one of these things to the positive first power. That's this piece right here, but then I have a plus c over this term. That's to the negative 9th power. So this right here is the general solution to this differential equation. But we're not done. I want to find c. How do I do that? The initial condition. So if I plug this in and set it equal to 100 and then solve for c, then I'll have my differential equation solution for the amount of salt in this tank, or the amount of, what is it, additive. So apply the initial condition. So plug 0 in and then solve this, or set this equal to 100 and then solve for c. So when I y at 0, so plug in 0 here for t, so minus, I'm going to get in this first piece right here. Well, that's going to be minus 5 times 0, which is 0. So 2,000 minus 0, it's 2,000 times 4, or 2,000 times 2, which is 4,000, plus what? So I'm going to have, so this will be 2,000 to the negative 9th power times c, right? So this will be c over 2,000 to the negative 9th power, and that's going to be equal to 100. So now when you solve that for c, you're going to have 4,000 right? So how do I subtract 100 from both sides? Or you could bring the 4,000 over here, it doesn't matter. So I'll subtract the 4,000 from both sides. So you'll have c over 2,000 to the negative 9th power. I'm just keeping it this way because this is a very big number, right? 2,000, if you rose that to the 9th power, that's going to be big. So I'm just keeping it that way. And that's going to equal 4,000 minus 100 is negative 3,900. Then multiply this by both sides. So you get c equals negative 3,900 times 2,000 to the negative 9th power. So there's the constant c. I'm leaving it that way. I'm not, you know, if you pop that number in your calculator, you're going to get a big number. I'll show you. I don't even know if your calculator can do it, to be honest. Oh, yeah, I can. But it's obviously a very big negative number. This is over 27 places, so we just leave it that way. Alright, so when it's all said and done, my specific solution, right, or my explicit solution is going to be this with c, that. So y as a function of t is 2 times the quantity 2,000 minus 5t. Now since c is negative, I'm going to write this as minus this over that. So it'll be minus 3,900 times 2,000 to the negative 9th all over 2,000 minus 5t to the negative 9th. And if you want, you could, I would just leave it this way, but this right here is the function that measures This right here is the function that measures the amount of salt, or amount of stuff. In this case, it was what? In this problem, the amount of stuff was additive, so that's the amount of additive at time t. Wow. And that problem was a lot of endurance, wasn't it? So yeah, that's the amount of additive at time t. Now, technically we're not done yet, because the answer to the question was what? How much additive is in the tank 20 minutes after the pumping process begins? So the final answer is plugging 20 in here. So how much after $20 minutes? Just plug 20 in there. So when you plug 20 in here, and that's just a simple, that's just a basic plug and chug, right? So when you do that, again, let me just make a comment on here. If you want to make these exponents positive, you could do that. Just bring this down here and then bring this up. You don't have to, but that right there is, this is the explicit solution. You don't have to do that, but you could. This is the general solution, this is the explicit solution. So if you plug that in here, if you go through it, I'll attempt to type it in my calculator. So I have 2 times the quantity, 2,000 minus 5 times, what was it, 20? I'm putting in here, yeah, 20. So that's the first piece, minus parentheses for 3,900 times 2,000 to the negative 9th power. That's the numerator of this, right? Divided by the denominator is 2,000 minus 520. I think I should put another set of parentheses in here. There we go. And that's going to be so that to the negative 9th, and then divide that. So yeah, that's the denominator of that. Here's the numerator, and there's the first term. So I'll cross fingers when I go through that, hit enter. You get approximately 1342. So that's how much additive after 20 minutes when the pumping process starts. Roughly 1,342 pounds. Oh boy. So yeah. These problems, when it comes to making the differential equation and then solving it, finding the integrating factor, multiplying up both sides of the integrating factor, and then integrating the right side of it, and then you get that, and then find the constant C for the explicit solution. Yeah, these problems, there's a lot to them, I'm not going to lie. But if there's any silver lining I can, if there's anything that I could help you, if you're overwhelmed with this, is to practice it with the homework. But another thing is that a lot of these problems while they look like this and they are lengthy, it may not be as difficult as this one. Some of them could be actually really efficient. Some of them could be really quick. This one in particular was a little more extensive, but not all of them are this lengthy. I'll just say that. But so yeah, don't worry too much, but at the same time, you should also practice how to do it. And there are no promises. Like sometimes you will get ones that are this involved and could have a lot of work to it. But there are other examples out there that are really, really not that bad. They're a little bit more efficient. So when it comes to doing applications with word problems, that's the only thing I was going to look at in this section. So when I do 9.4, I'm just going to show you how to the last section, chapter 9, will be looking at long-term behavior of a differential equation. We kind of did it earlier in the chapter when we did slope fields and stuff, but this one we're going to look at, it's very similar to something you looked at in Calc 1, but yeah, you'll see what I mean. So we'll look at that in the next section.